Hello everyone. In this video, I will solve GET Physics 2022 question number 56. A particle of mass m in the xy plane is confined in an infinite two-dimensional well with vertices at 0, 0, 0L, LL and L0. The eigenfunctions of this particle are psi nx ny equal to 2 by L sine nx pi x by L sine ny pi y by L. If perturbation of the form v equal to cxy, where c is a real constant, is applied, then which of the following statements are correct for the first excited state? So there could be more than one option correct. So using the time independent perturbation theory, we will have to solve this for the first order correction for the first excited state. Okay, so for the first excited state, not ground state. So the eigenfunction nx ny is equal to 2 by L sine nx pi x by L sine ny pi y by L. This is our eigenfunction, and we know that for 2D infinite potential well, the unperturbed energy, eigenenergy is nx square plus ny square pi square h bar square divided by twice m L square. Now for the ground state, nx and here nx and ny belongs to 1, 2, 3 and so on. So for the ground state, obviously nx equal to 1 and ny equal to 1, and this is not degenerate. But for the first excited state, we can have two conditions: nx equal to 1, ny equal to 2, and nx equal to 2, ny equal to 1. So this is doubly degenerate, the first excited state. This was the first excited state. For both this condition, the energy is equal to E naught equal to 5 pi square h bar square by twice m L square. And the ground state energy, which is this is the ground state, and the ground state energy is 2 pi square h bar square by 2 m L square. Now to solve the degenerate perturbation using this degenerate perturbation theory, we will solve this. So we have to first solve this matrix element, where WAA is psi A naught h dash psi A naught, and WAB is psi A naught h dash psi B naught, and so on. So where psi A naught is psi A naught and psi B naught are the two eigenstates which are degenerate. So for the first excited state, we will have sine pi x by L sine 2 pi y by L. One is this and the other one is sine 2 pi x by L sine pi y by L, right? So these are the two states. So using these states, we'll calculate WAA. So basically we don't need to calculate it specifically, so let's say we can argue from the expression as well, where WAA will be this 0 to L sine square pi x by L sine square 2 pi y by L. The perturbation is cxy dx dy, and WBB is 2 by LL whole square 0 to L sine square 2 pi x by L sine square pi y by L, and the potential is C xy dx dy. So if you look in these two expression, you can see that WAA equal to WBB, because sine square pi x, and here it is x dx, and we this is the x integration, and here the y integration are similar, sine square pi y dy. So these x and y are just dummy indices for these integrations. And similarly here we have sine 2 pi sine square 2 pi y dy, and here we have sine square 2 pi x dx. So both of these two integration and limit are same, so the final result of these integrations will be equal. So obviously WAA equal to WBB. And if you see that W, and let's say this is A. Similarly, the off diagonal elements, which are WAB and WBA, they will also be same, and we call this as B, with this same argument, because this is x and y. So this perturbation h dash is cxy, so it is linear with both x and y. So that's why we can say that WAA and WBB are same. Similarly, WAB and WBA are also same. So our matrix will be A, B, B, A. So to find the correction to the first excited state energy, we'll have to solve for the eigenvalues of this matrix. So we'll have to find eigenvalue A minus delta B, B A minus delta. We'll have to solve this equal to 0. We have to solve this matrix and find delta. So this will be the correction to the first correction to the energy, first excited state energy. So which two options are correct? Option A says the unperturbed energy is this, which is not correct, because unperturbed energy is 2 pi square h bar square by 2 ml square. The unperturbed energy is 5 pi square h bar square by 2 ml square. Oh, sorry, for the first excited state, sorry, this is not the energy. The unperturbed energy is this. So option B is correct. And in option C, we see that the first order energy shift due to the applied perturbation is 0, but that is not true, because we have seen that we have to solve for this matrix and find out what delta is. So in option D says that the shift is in energy due to the applied perturbation is determined by an equation of the form this, where A and B are real non-zero constants. So option D is also correct. So option B and D both are correct for this question.